When we have a function and we'd like to find the limit of that function, what we're really looking for are the y-coordinates of points as the x-coordinates of those points get close to a value. So we've seen that we can find limits by looking at graphs or by making tables. We've also seen that we can find limits by direct substitution of a value if our function exists at that value that our x is approaching. If our function doesn't exist at that value that x is approaching, which is the case in this function, that we may still be able to find the limit through direct substitution if it's possible to simplify the function. And then looking at the simplified version of the function and directly substituting the value to find the limit. So in this case, what we see is that as the x-coordinates of the points along our function get close to 25, the y-coordinates get close to 1/10. The other thing that we've talked about is a definition of continuity. And we've said that if we'd like to know whether a function is continuous at a point, we need to determine if the limit as our x's approach that point of our function exists. We need to know whether or not the value of the function exists at that point. And if those two things are equal to each other, then we can say that the function is continuous at that point. If any one of those three things fails, then our function is discontinuous at that point. So for example, with this function, we want to know if it's continuous at x equals 2. It's pretty obvious from the graph that it isn't, because we have a hole in the graph that we would have to jump over. We'd have to jump down to the point at 2, 1, and then jump back to the graph if we were drawing it from left to right. But to use our definition of continuity, the first thing we would do is to see if we have a limit as x approaches 2, which we do because the limit from the left and the limit from the right are equal to each other. Then we would figure out what f of 2 is, and it exists, it equals 1. But since those two values aren't equal to each other, we can say that the function is not continuous at x equals 2. Let's look at this function. This is a piecewise function called g, and we'd like to know if this piecewise function is continuous at x equals -2. So we'll start with looking at the limit of g of x as x approaches -2. We'll have to look at a left-hand limit and a right-hand limit because this particular piecewise function separates at that value of x equals -2. So for the left-hand limit, the limit as x approaches -2 from the left, we'll have to look at this first part of the function because it is defined for all x-coordinates that are less than -2. And if we're approaching -2 from the left, that means our x-coordinates of our points are less than -2. Now, since that particular part of the function is a polynomial function, which is defined for the value of x equals -2, we can directly substitute -2 to get the value of our limit, which is 2. For the right-hand limit, the limit as x approaches -2 from the right, we'll look at this second part of the piecewise function because it defines the function for x values that are greater than or equal to -2. And if we're approaching -2 from the right, our x-coordinates are larger than -2. Once again, this part of the function is a polynomial function that's defined at x equals -2, so we can directly substitute -2 for the x to get a limit of -3. Now remember, we're trying to find the limit as x approaches -2, And what we've seen is that the limit from the left is 2 and the limit from the right is -3. And those two are not equal to each other. So the limit as x approaches -2 of our function doesn't exist. And since the limit doesn't exist, we can stop at this point and conclude that the function is not continuous at x equals -2. Now here's what a graph of that function looks like. This part of the function, which is really the line y equals 1/2 x plus 3, is defined for x less than -2, which is why it's only this part of the line. And the lower part of this piecewise function, which is part of the line y equals x minus 1, only contains the part of that line that has x coordinates that are greater than or equal to -2. And it's pretty clear from the graph why our function was discontinuous at x equals -2. That's where we had the jump in the graph. The two ends did not meet at a point where x was equal to -2. Another concept we've talked about already is the idea of what slope is. For linear functions, slope is a ratio of the vertical change between 2 points on the line and the horizontal change between those 2 points. So we said to find the slope, we could find the difference in the y-coordinates of the 2 points and divide that by the difference of the x-coordinates of the 2 points, which is something we called a difference quotient. So let's suppose we have this curve. This one is a parabola. What we would like to find is the slope of the line between the 2 points that are on the curve. Well, a line that goes between 2 points on a curve is called a secant line. So if we'd like to find the slope of that secant line, all we have to do is find the difference of the y-coordinates and the difference of the x-coordinates of the 2 points on that curve. That's really no different than what we've done any other time we find slope. But in this case, those 2 points that define the secant line are points that are also on the curve. Now what we're going to call that is the average rate of change. The average rate of change of y with respect to x, as x changes from x sub 1 to x sub 2, is the ratio of the change in y-coordinates to the change in x-coordinates. So remember, if we're trying to find an average rate of change, we're simply finding the slope of a secant line between 2 points on the line. So let's look at this function. Our function is f of x equals x squared, and we would like to find the average rate of change as x changes from 1 to 3. So what we need are x and y coordinates of 2 points. The first point has an x-coordinate of 1, and to find the y-coordinate, we'll substitute 1 in our function for x, and get 1 squared, which is equal to 1 for y. So our first point is 1, 1. Our second point has an x-coordinate of 3, and its y-coordinate is what we get when we substitute 3 in for x in our function. 3 squared is 9. So our second point is 3, 9. So to find the average rate of change, we simply have to find the slope of the line between those 2 points, which is 4. Here's a graph of that function with the 2 points shown in the graph and the secant line drawn between the 2 points. The first point was 1, 1. We knew the x-coordinate. We found the y-coordinate. And the second point was 3, 9. Once again, we knew the x-coordinate was 3, and we found the y-coordinate. So to find the average rate of change, all we did was find the slope of the secant line that contained those 2 points. Now let's generalize this a little bit. Let's say we want to be able to find the average rate of change between any 2 points on the curve. we're still going to have to find the slope of a secant line. And we're going to have to know something about the x and y coordinates of those two generalized points. So the first point has some x coordinate, and the y coordinate that would go along with that point is f of x, because it's on the curve y equals f of x. The second point also has an x coordinate, but let's say what we know is the distance between the first x coordinate and the second x coordinate. And we'll call that distance h. That means that the second x coordinate would be x plus h, and the y coordinate that goes along with that x coordinate is f of x plus h, because it's also on the curve. So to find the average rate of change, we're finding the slope of the secant line between those 2 points. The left point is x, f of x, and the right point is x plus h, f of x plus h. Now we know to find the slope of the secant line, we simply have to subtract the y coordinates of the points and subtract the x coordinates and find that quotient. And if we simplify that fraction, we'll have this one, f of x plus h minus f of x, all divided by h. That's our difference quotient for finding the average rate of change between any general points on the curve. So let's use that difference quotient for this particular function. F of x is equal to x squared, and we want to find the difference quotient when x is 5 and h is 3. Well, the difference quotient is this, f of x plus h minus f of x over h. Remember, it's really just a slope formula. It's just a generalized slope formula. We know that x is 5 and h is 3. And we certainly know that 5 plus 3 is 8. So in the numerator, you'll see we still have a little bit of work to do, because f of 8 means we need to find a value when we substitute 8 into our function, and f of 5 means we need to find a value when we substitute 5 into our function. And since our function is f of x equals x squared, f of 8 is 8 squared, and f of 5 is 5 squared. 8 squared is 64. 5 squared is 25. If we subtract in the numerator, we have 39, so 39 thirds, which simplifies to 13. So the difference quotient when x is 5 and h is 3 is 13. So think about what we just found. 13 is a difference quotient, so it's a slope of a line. It's a slope of a secant line that connects 2 points on the graph. Those 2 points on the graph have an x-coordinate of 5 for the first point and an x-coordinate of 5 plus 3, or 8, for the second point. So the slope of the line between those 2 points on this curve is equal to 13. Let's try this one. For f of x equals 1/4 x squared, find the difference quotient when x is 2 and h is 3. So here's our difference quotient, f of x plus h minus f of x over h. X is 2 and h is 3, so we need to find f of 2 plus 3 minus f of 2 over 3, which means we need to find f of 5 minus f of 2 over 3. To find f of 5, we substitute 5 into our function for x, and to find f of 2, we substitute 2 into our function for x. Make sure you follow order of operations and you square first, and then we can subtract the fractions. 25/4 minus 4/4 is 21/4, and 21/4 divided by 3 is the same thing as 21/4 times 1/3, which is 7/4. So the difference quotient, the slope of the line between these 2 points, is 7/4. Now here's what the curve looks like. This is a graph of y equals 1/4 x squared. Our first point had an x-coordinate of 2, and the y-coordinate was 1. The second point had an x-coordinate that was 3 units bigger than 2, which was 5, and a y-coordinate that was f of 5, or 25/4. So we found the slope of the line between those 2 points was 7/4. That's called the difference quotient, and it's also called the average rate of change. So what you see is that for the most part, what we're doing with average rate of change is nothing more than finding the slope of a line between 2 points. The notation looks a little bit different, and the terminology is a little bit different, but it's something that's very familiar to you.